So, now let us look at a little bit in detail about P450 catalyzed transformations. So, P450 are heme proteins, that is they contain heme and iron, and we will look at some of these details in the subsequent lectures. And they catalyze a reaction that splits molecular oxygen. We already saw that in the previous slide, and one of the oxygen atoms is introduced to the drug. So, the drug starts out as drug and ends up as, so you have a drug H and it ends up as drug OH. So, this is the OH that is added, and so these enzymes are known as monooxygenases. Okay. So, there are 33 different types of cytochrome P450 and they are classified into 4 families, that is CYP1 all the way to CYP4, and each of these families is again further divided and designated by letter. So, for example, you can have CYP2A1 or CYP3A4 and so on and so forth. Okay. Most drugs are currently in use are metabolized by 5 primary enzymes. So, you can bring down that large number down to pretty much 5 numbers. So, that is CYP3A, 2D6, 2C9, 1A2 and 2E1. Okay. This particular enzyme CYP3A4 is quite important in metabolism and it is responsible for metabolism of most drugs. So, therefore, this is something that we should keep in mind when we are designing a drug. So, the drug can be very easily tested with this enzyme to see how stable the drug is, even during its discovery phase. Right. So, oxidation of carbon atoms can occur if the carbon is exposed, that is if it is easily accessible or if it is activated. Right. So, for example, methyl groups R CH3 can undergo oxidation to form R CH2 OH, which then can subsequently be oxidized again to an aldehyde, which will undergo oxidation to form a carboxylic acid. Okay. So, these are the sequence of reactions that can occur on a terminal or an exposed methyl group. Okay. It can also happen where you have R CH2 CH3, that means you have an ethyl group which can get converted all the way to R CH2 CO OH. Right. Eventually, the products of oxidation is going to be carboxylic acids, which are going to be soluble and they can be excreted through the urine. When you have longer chains, the terminal carbon and the penultimate carbon are the most exposed and they are both susceptible to oxidation. So, we just looked at the example of the terminal carbon, but now imagine you can also have that you can have an internal carbon which can undergo oxidation. So, let us say you have this molecule here, this can form R CH OH CH3, which in turn can undergo oxidation again to form R C double bond O CH3. So, you are generating a ketone. In a cyclic system such as an aliphatic ring, the most exposed region is more likely to be oxidized. So, if you have an example of a cyclohexane ring as shown here, it can undergo oxidation to the corresponding alcohol. Okay. You can also have sp2 centers, and these sp2 centers are like allylic or benzylic positions can be susceptible to oxidation and they are more likely, or if they are also next to an sp carbon center. So, let us first look at the case of an sp2 carbon center. So, you have a benzene ring which has a methyl group on it and you have some other functional group on the left hand side, and what can happen is this undergoes oxidation to give you the corresponding benzylic alcohol, which then can undergo steps of oxidation to give you correspondingly the benzoic acid. Okay. So, this is fairly straightforward for us to understand. It is also possible that you have an olefin such as this. This is an allylic position which can undergo oxidation to give you R prime, okay. And you can also have oxidations next to the ketone. So, for example, you have R C double bond O CH2 R prime. Now, this position here is quite susceptible to oxidation, and so you can have R C double bond O CH OH R prime, right. And as I mentioned earlier, you can also have similarly the sp carbon, which is basically a carbon carbon triple bond, which will form CH2 R prime, can undergo oxidation to R C triple bond C C OH R prime. Okay. So, these are the major reactions that one could expect with in the case of sp2 or sp carbons. Now, when the carbons which have an alpha, which are alpha to a heteroatom, are also activated, and they are also more prone to oxidation. So, the example that we are going to look at is R CH2 NR R. This can undergo oxidation. This center is quite susceptible to oxidation, and so you have RCHOH, right. So, let us say you put a prime over here, and this is going to be the product of oxidation, but this product is not very stable, okay, and this is going to further undergo hydrolysis to form an aldehyde and an amine. In this case, it will form a secondary amine. So, the product of this oxidation is actually an aldehyde. Now, you can actually extrapolate this to other heteroatoms as well, and you can look at, for example, a ether. So, you have R CH2O AR, which can undergo oxidation to give you R CH OH OR, and now this is quite unstable. You can push electrons, kick out the alkoxide, and you will form R C double bond O H. And so, we have looked at AR here. So, we will stick to the same convention plus AR OH. Okay. So, these are again possible. Similarly, you can do the same thing with thiols, right. You have thioethers which can again collapse to give you the corresponding aldehyde and a thiol. So, for example, you have R CH2 S R prime. I am not going to draw the arrows, you are going to form R CH O plus R prime SH. Okay. So, this is the other way in which we can do this metabolism. So, the product in all these cases is an aldehyde, okay. And so, we have already looked at that aldehyde can undergo oxidation to produce the corresponding carboxylic acid, okay. And the result of this whole process is dealkylation of amines, ethers or thioethers, and we have not looked at it, but dehalogenation of alkyl halides can also occur. So, the way in which dehalogenation of alkyl halides occurs is in the following way. We have R CH X R prime, which can undergo oxidation to give you R C OH X R prime, and now you can push arrows in the following manner to give you R C double bond O R prime plus H x. Okay. So, dehalogenation of alkyl halides is also possible to give you the corresponding ketone. Tertiary amines are found to be more reactive to oxidative dealkylation than secondary amines. Okay. So, I am not going to spend a lot of time on this, but we already know that basicity plays an important role. So, tertiary amines are these, which are definitely more reactive than the corresponding secondary amine and so on, right. While O demethylation of aromatic ethers is faster than O dealkylation of larger alkyl groups. So, if you look at it, O demethylation, that is breaking here, is much faster than O dealkylation. So, if we compare this with the same O dealkylation with the ethyl group, this is slower than that of a methyl group. So, cytochromes can also oxidize olefins and other unsaturated bonds to form epoxides. Okay. So, let us look at what the reaction is. So, you have R, let us say we have a double olefin like this. In the presence of cytochrome P450, this can actually undergo oxidation, epoxidation to form this kind of molecule. Okay. Now, there is an enzyme called as epoxide hydrolase, which opens up this epoxide and forms R C OH, C OH R. Okay. So, this is not indicative of stereochemistry here, but this is the product that is formed, which is a diol. But if the epoxide evades this enzyme, right. So, that means if the reaction does not happen quickly enough, then this center is a very good center for attack by a nucleophile. So, what can happen is that this ends up into an alkylating agent. Oxidation of aromatic rings can also happen, and so you have a couple of possibilities here. So, let us draw out a benzene ring. So, this reacts with cytochromes P450 and produces the corresponding epoxide. Let us say this carbon bond undergoes epoxidation. Now, the straightforward way to do this is if you add water across the epoxide, you are going to get the corresponding diol. And so, let us say the attack happens from the top, the other oxygen ends up in the bottom, and the rest of the molecule remains the same. But it is also possible that you have a hydride shift that can occur. So, you can think about the hydride shift like this, and it gives you the corresponding phenol, right. So, these are the two possibilities that can really happen, and if you have a substituent on the para position, that is over here, you typically favor the formation of the para alcohol, right. And electron rich aromatic rings are likely to be epoxidized more quickly than the ones with electron withdrawing groups on it. And we will look at some of the mechanisms of these oxidations very soon. Okay. But we need to keep this in mind, because we have to factor this while we are designing a drug. Okay. Tertiary amines, as we looked at, can also be oxidized to N oxides, okay, as long as the alkyl groups are not sterically demanding, right. So, the reaction that we are looking at here is R N. Let us take the example of methyl groups CH3, it is going to get oxidized over here to form R N O minus CH3. These are known as N oxides, and primary and secondary amines are also oxidized to N oxides, but these rapidly convert to hydroxylamines and beyond. So, the reaction that we are looking at here is R C H R prime NH2, and now this can undergo oxidation to form R C H R prime NH OH, right, and this can actually form what is known as an imine by further oxidation, and it will give you R prime R double bond N OH. It can form an hydroxylamine, for example, which can subsequently get converted to a nitro group. Okay. So, this can also be at the terminal carbon can be attached to the amine, and you will correspondingly form the terminal carbon with a nitro group. Aromatic amines are also oxidized in stages, and so we will look at if you have an aromatic amine such as aniline, this can further get oxidized to form OH, which can then give you correspondingly the nitroso group, which will then form finally the nitro group. Okay. So, some of these intermediates such as nitrosobenzene is actually quite electrophilic, and they can alkylate proteins or nucleic acids. So, anilines are some things that can be potentially quite toxic to incorporate in a drug. Primary and secondary amides can also be oxidized to the corresponding hydroxylamides. So, when you have R C double bond O NH2, these can also undergo oxidation to form R C double bond O NH-OH, and these are some functional groups that have been associated with toxicity and carcinogenicity. And so, one needs to understand whether an amide that is going to be formed has a propensity to form this kind of intermediate or not. Okay. You can also have secondary amides R C double bond O NH R prime, which can then undergo oxidation to give you R C double bond O N OH, and this R prime is intact, right. So, this is also possible, and so this is something to keep in mind if you are going to have an amide as a functional group in your drug. Sulfur containing functional groups can also be oxidized. So, let us say you have a thiol, we have already looked at this, this can undergo oxidation to give you RSSR, which is basically a disulfide. You can also have thioether, which can give you RS double bond O, which is a sulfoxide, right, which can then subsequently be oxidized further to form RS double bond O R, which is basically a sulfoxide. Okay, so, all these are possible. If your drug has a thiocarbonyl compound such as this, then you can also have oxidation, you can have a desulfuration to give you a ketone. So, these are some of the fates that we can expect of sulfur containing compounds.